Hello everyone. Today we will have lecture 37. Since now we have been talking on several aspects of thermodynamics and kinetics of electrochemistry. In thermodynamics we have looked at Pobe diagram, and in the kinetics part we actually looked at polarization, which is the manifestation of current flow during electrochemical reactions on a metal surface. And when we have looked at the polarization part, we saw that it actually relates kinetics of rate of transformation of metal into ions or ions into metal with the voltage. So, the voltage part is talking about thermodynamics and the current is actually looking at the kinetics. So, it is basically a relation between kinetics and thermodynamics. And then now today actually we will step into the aspect which is called mixed potential theory. In the mixed potential theory, which is basically a very modern theory to understand corrosion, and here you would be able to see that yes, it can allow us to understand why that different kinetic factors like exchange current density, one is exchange current density, of course, if it increases as a function of galvanic coupling between active metal with a noble metal, and the exchange current density of hydrogen evolution reaction, if it increases on those active components, we would see that the metal dissolution increases to a great extent, that active component dissolves quickly. Even in case of zinc, we have seen three examples that if we have pure HCl without any oxygen in it, then we have some rate. If we have oxygen in it, we see that the rate increases, and if we have one more the impurity in the form of ferric ion, we see that the corrosion rate of zinc increases enormously. So, this particular theory can explain it better, that why those changes in corrosion rate of zinc happens due to those kinetic factors as well as the environmental factors coming into the picture, coming into consideration while considering the corrosion of a particular metal. So, today we have lecture 37, and we will still continue on kinetics of corrosion, and eventually we will get to the modern theory of mixed potential theory. Now, as we have seen that the polarization has two components, activation plus concentration, and the activation part can be related with beta log I0, and this one can be related as 0.591 n log 1 minus I by I max. And this I max in different books, sometimes it is written as I max or sometimes it is written as IL, which is nothing but I limiting. Limiting current density. Now, apart from that, there is one more polarization. Because of that, the potential can shift from equilibrium potential to other potential, or the stable potentials to other potential. That particular polarization we call it resistance polarization, which is neta over voltage resistance, is basically nothing but IR drop. That resistance of the circuit, which will lead to some drop in voltage in the form of IR. I is the current, and that polarization is called resistance polarization. But in case of corrosive environment, when we see that the metal is put in or immersed in an electrolyte which has sufficiently very high conductivity, and that is what that IR drop in kind of conducting electrolyte is very small, and that is what we will not be able to consider this IR drop in our common corrosion processes, but definitely we will talk about over voltage due to activation and over voltage due to concentration effect on the corrosion of a particular metal. And now if I try to plot these two particular polarization, remember this beta I by I 0, I can write either A, which is activation, or C, which is A is anodic, C is cathodic, and here also accordingly we can write A or C. I 0 is nothing but the exchange current density, and here N is the number of electrons participating in that redox reaction. Now if I try to plot, the plot nature as we have seen before would be like this. If I try to plot this one, this is over voltage, this is log I, and if this is the point where over voltage is 0 and corresponding to I 0 of that particular metal, and if I try to plot this, this plot will look like this. This is the plot pattern. Now if I try to plot this one, same neta here is equal to 0, neta over voltage is 0 corresponding to I 0, and this plot would look like this corresponding to beta C, since we are considering cathodic over voltage. Now if I try to see the total over voltage, so we have to just combine these two. So the combination of these two would be, so this is the point neta equal to 0, I 0 equal to, this is the point which corresponding to log I 0, and this axis is log I, this axis is also log I. Now once we combine, the combination curve will look like, so if I combination curve will look like this. So this part is activation and this part is concentration polarization. And we have also seen that this concentration polarization actually depends on several factors. Of course, the metal type of metal, metal surface, agitation, temperature, all those will have effect on this I max. This particular current is I max, since once I max is reached, you see that this over voltage becomes infinitely large. So that is what the when it reaches I max, it actually drops vertically with reference to the log I axis. That means this point is also I max. Okay. Now if I try to see one factor, let us say agitation, let us say I increase the velocity. If I increase the velocity, because of the churning, it could lead to temperature increase, and once temperature increases, diffusivity increases. Now and once I increase the velocity, if I try to look at the boundary layer as well as the way concentration is changing. So this is the IHP, OEHP, and we have seen the concentration is changing like this. This is the bulk concentration, and if this is the C, so then this is my diffusion distance delta or boundary layer thickness, and then if I increase velocity, of course I am seeing temperature increases, and if temperature increases, diffusivity increases. Now if agitation increases, then or the velocity increases, delta decreases, and interestingly concentration polarization. The cathodic current side 0.0591 by N log 1 minus I by I max you could see that this I also related to minus dNf C0 minus C divided by delta, and I max is equal to minus dNf C0 by delta. Now, for a particular process, reduction process, N and F are constant. Now, because of this velocity increases, I am increasing this, I am increasing temperature, and due to this d is increasing, delta is decreasing. So, I max also, so if I try to write here, so I max increases. Now, interestingly, if I max increases, then I would have also corresponding change in the polarization response. Now, you could see that combination of those two situations, one is activation and another one is concentration, and this is the combination of these two. Now, here if I try to see the combination, first it will go like this, which is activation part, and then concentration part would increase this particular polarization, which is cathodic side. This is I0 and corresponding to neta equal to 0. Now, as the I max is increasing, that suggests that this I max would go to the right direction. So, now I max would appear at new position. So, now if this is my I max, so then this activation polarization would still extend till I max is reached in the second case. So, now this case it is velocity 1 and this case it is velocity 2 and V2 greater than velocity 1. So, I max increases, and that is what this curve is switching to the new position, which is this one. Now, if your velocity increases further, so I max will again switch to the right. So, then we will have another new position of I max. Let us say this is my I max when V3 and V3 greater than V1 as well as V2. So, this activation polarization part would still increase further. Now, interestingly, you could see that as we are increasing velocity, because of these factors we are increasing I max, and that is what that polarization curve is switching to shifting towards right. That means, the I max appearance of I max is shifting towards right. This situation will be explained, will have strong effect on corrosion of metal. We will see later that actually after certain time, after certain velocity, in some metal corrosion, we see that the corrosion of metal initially increases and then it becomes stable or constant corrosion rate. So, that will be explained with the help of mixed potential theory. So, this is one factor. The second factor, sometimes we have combination more than one cathodic reactions. For example, if a system has got dissolved oxygen, then and if that system is acidic, so we can have this reaction. This cathodic reaction, as well as since it is acidic, so we can have this reaction also. Now, here the standard reduction potential is E0 equal to 0 and here E0 equal to 1.227 volt. If I try to see the response of cathodic polarization as well as what happens in the concentration as well as activation polarization regime, we can have a response like this. This is log I, this is over voltage. Now, if this is neta for oxygen reaction is equal to 0 at this point, and corresponding to the potential which is E0 equal to 1.227 volt. Remember, this is the equilibrium voltage, and at equilibrium voltage we have over voltage to be 0 for that oxygen reduction. And if I try to see if E is equal to 0 here, then it corresponds to neta H2 evolution to be 0 at this point, and let us say this is the, I switch this particular plot little down. So, then only we will be able to see the variation. This is log I, this is I0 for hydrogen reaction, this is I0 for oxygen reaction. Now, for oxygen it will have its own cathode activation polarization. Let us say this is my activation polarization of oxygen reduction. Now, let us say this is my I max for oxygen reduction. So, that means it cannot go, it can come to this point, up to this point, and then it will take this particular path. So, this path is out as per our understanding. Now, for once it is going towards cathodic polarization regime and it is polarized, over voltage is increasing gradually. Now, this hydrogen reaction also has got its own activation polarization. If that one moves like this, so then if it comes like this, because once I max is reached for oxygen reduction, it will fall rapidly almost perpendicular to the log I axis, and then it will experience the activation polarization of hydrogen reduction. And hydrogen ion, if I consider H plus ion diffusivity, DH plus let us say, and if I consider DO2, so DO2 is actually less than DH plus, then correspondingly I max O2 reaction O2 should be less than I max H plus ion, considering that fact that delta and C0 are fixed. Of course, temperature is also fixed. I am just seeing the size of those particular molecules. Since it is a very small size, that is why its diffusivity would be very fast. So, that case I max should be high for H plus ion. So, that means if I try to, without considering this oxygen polarization part, if I try to look at only the hydrogen polarization part, it will have its own polarization and then finally it will reach its I max H plus. So, the curve pattern would be, since it is polarization is starting from a higher potential from oxygen reduction. So, it will fall like this. If I try to draw it with a different color, so this particular fall would be like this, it will follow this pattern and then it will switch to this pattern and then follow like this. So, this red color lines would be the actual polarization line for both the reactions. If I can go up to a very high over voltage or very great bit of polarization, of course, in the cathodic side. So, this also has got relation with the on the diffusivity part, and finally, it is basically this equation which is governing this kind of I max variation, which is minus d NF C0 by delta. So, this is about concentration polarization as well as activation polarization and how in combination how they would look. Now, let us get to the fundamental of mixed potential theory. Whatever understanding we have on kinetics of corrosion, that part will be now used for understanding corrosion events, and then you will see that yes, whatever understanding we have whatever fundamentals we are going through, they will be really useful in corrosion events. This mixed potential theory is, as we have mentioned, that it is a very modern theory, and it starts, it actually it was known way back in 1990, in 1900, and but it was proposed and formalized by two scientists, C. Wagner and W. Troud in 1938. This was formally formulated, I would say, and they had a famous paper in Journal of Electrochem. It's 1938 publication. This is on the interpretation of corrosion process through the superposition of electrochemical partial processes and on the potential of mixed electrodes. So, if I try to see the paper name, it says on the interpretation of corrosion processes through the superposition of electrochemical partial processes and on the potential of mixed electrode. Interestingly, if you see this corrosion processes through superposition of electrochemical partial processes, this is very important, partial, and also on the potential of mixed electrode. Now, if I could get back to the corrosion of zinc in pure deaerated dilute HCl solution. So, this is a beaker and where I have put HCl, which is pure deaerated and dilute solution. In that case, I have put a zinc piece, and immediately I could see that hydrogen bubble will form on the metal surface. Now, if I analyze this, I will see that the actual process is this is the actual reaction that takes place. Interestingly, this is a full redox reaction, and here, so this full redox reaction, in case of instead of processes, I could see that this is a single process. This redox reaction can be broken into one oxidation and one reduction process. So, thus oxidation is, this is the oxidation or anodic process, or I could say corrosion process, and the second part is H plus 2E equal to H2. So, this is cathodic process. So, that means the first statement which says the corrosion process through the superposition of electrochemical partial processes. Now, you see that this one full redox reaction has been broken into two redox reactions, two reactions, partial reactions, one is oxidation, another one is reduction. Now, instead of that, if we have ferric ions, then of course, there could be one more reduction process, which is plus 3 plus 1 electron, it go to plus 2. So, this is another cathodic process. So, that means whenever, and actually the anodic process is this one, which is the corrosion event. The corrosion event is single corrosion event, but you have that entire process has been divided into three partial reactions, one anodic and two cathodic. So, from there the first hypothesis has been drawn. So, this says that any electrochemical reaction can be divided into two or more partial oxidation and reduction reaction. Now, the second, this is the first hypothesis by from C. Wagner and W. Trout in 1938. This is the hypothesis of mixed potential theory. And the second hypothesis, they are saying that the what they are saying in the title is potential of mixed electrode. In fact, that potential of mixed electrode or the mixed potential of electrode will be achieved due to these reactions, due to these partial reactions, and when this mixed potential of electrode is attained due to these reactions, partial reactions, it says that there will be no accumulation of charge, or in other words it says that laws of conservation of charges. So, now we see that there is one cathodic reaction, there are two. For example, if I consider this particular reactions, I could see that there are one cathodic and one anodic reactions. So, if there is no accumulation of charge, net accumulation, rather I would say this net part, net accumulation. So, that means that all the charges are balanced. That case I must say this, for example, for this reaction there could be a current called IA, because this is the anodic current density for anodic process, and this, for this reaction there should be IC, which is the cathodic current or current density I would say. So, that case IC should be equal to IA at mixed potential. So, this is the second hypothesis. So, on these two hypotheses we will start looking at the understanding of corrosion events in our next lecture. Let us stop here. Thank you very much.